All right, so last time we talked about Lewis structures. We learned how to draw Lewis structures, and we said that oftentimes there's more than one way to draw a valid Lewis structure that follows the octet, okay, or duet rule. Let me turn off your mic for a while because I'm. All right, so we said that oftentimes there's more than one way of drawing a Lewis structure, and one way you can determine which of the structures are more feasible than others is by looking at formal charges. And so here's an example. Let's say you have a molecule that's made up of 1 carbon, 4 hydrogens, and oxygen. Okay, if you look at these 3 structures down here, you can see all of these follow the octet rule. Look at carbon right here, for example. It says 2, 4, 6, 8. All right, so it's got 8 valence electrons around it. This oxygen has 2, 4, 6, 8 valence electrons around it. Same thing for the carbon and oxygen in the other structures. And if you look at all the hydrogens, they all just have a single bond. Okay, so they all have a duet. But there's only one molecule in nature that has a formula of CH4O, so it's only one of these actually exists in nature. So how do you decide, okay, which is the most likely one? We said that we look for structures that have as low formal charge as possible. So the closer you are to 0 for formal charges, the better. In fact, if you have a +2 or a -2 and beyond that, it's very unlikely that that's going to be a reasonable representation of reality. Okay, so let's take a look at this one right here. Let's look at the formal charge for carbon here. We say the formal charge is equal to the number of valence electrons that the atom would have if we were free by itself minus what it appears to own in the structure, which is going to be half of what it's sharing plus everything that is in the lone pair. So in the case of carbon here, you have a formal charge equal to, okay, a free carbon atom belongs to group 4A, right? So 4 minus, it owns 2 of those 2 in the lone pair, and half of the 3 pairs. So 1, 2, 3 pairs. Half of the 3 pairs would be 3 singles, right? So formal charge in this case is 4 minus 5, which would be -1. All right, so if you go look at if you figure out the formal charges here, you'll find that this is going to be -1, that's +1, okay? And all the hydrogens here have a formal charge of 0. Carbon here has a formal charge of 0. Oxygen here has a formal charge of 0. Carbon over here, okay, would have, if you were to do that, let's see, 4 by itself. Okay, and it appears to own, in this case, 2, 4 in the lone pairs plus half of the bonding pairs. So half of 2 pairs would be 2 singles. So this carbon right here, 4 minus 6, would have a formal charge of -2. Okay, and this oxygen here would have a formal charge of +2, if you figured it out. Okay. So you can see the most likely structure of CH4O, if you'll find it in nature, is going to be this structure right here. In fact, this is what's experimentally found, that this is the way the atoms in CH4O are connected. This is methanol, okay? Methyl alcohol. All right, so let's just skip a few of the questions. Let's talk about skeleton structures that you might find. I think if you had a printout of the PowerPoint I posted, there was a typo there. I put aspirin as the example, and I changed the structure. So it's actually glycine, the one that you're seeing here. Okay. So skeleton structure is commonly drawn for organic molecules. We said organic molecules are molecules made up of primarily carbon and hydrogen and a few other nonmetals like oxygen and nitrogen. It's mostly carbon and hydrogen. So these are hydrocarbons, molecules made up of carbon and hydrogen only, or molecules that you can think of as being derived from hydrocarbons. So when you draw these skeleton structures, okay, Unless otherwise specified, when you see a line segment, at the end of each of those line segments, there's a carbon atom implied. So this corner right here implies that there's a carbon atom there. Okay, so I'm just gonna draw a carbon atom here. I'm gonna write C. This right here, okay, intersection of line segments, that's another carbon atom right there. Okay, now at this end of the line segment, you have an oxygen, the symbol for oxygen drawn, so that means that's not a carbon atom, that's an oxygen atom there. And so those are the implied carbon atoms in this skeleton structure. Now, atoms in a skeleton structure are assumed to have a zero formal charge unless otherwise indicated. So here, for example, this nitrogen right here, there's a plus next to it. That means that nitrogen has a formal charge of +1. And this oxygen right here has a negative sign next to it. That means that this particular oxygen atom has a formal charge of -1. Okay, so how do we actually complete, how do we actually complete this structure? Well, what that means is this. Remember we said carbon atoms, okay, they get a formal, by itself, a carbon atom by itself has 4 valence electrons, so it can get a formal charge of 0 anytime carbon forms 4 single bonds, okay, or 4 bonding pairs. That means a double bond and 2 single bonds, or it can form a triple bond or a single bond, or it can form 2 double bonds. So anytime you have carbon with 4 bonding pairs around it, it has a formal charge of 0. So that means the hydrogen, okay, that means this carbon right here has 2 other bonding pairs. Let's draw that carbon again. This particular carbon has already 1, 2, so there must be 2 more bonding pairs to that carbon. So those are implied. That this particular carbon implied in this corner has 2 other bonds, and those are bonds to hydrogen. All right, what about this carbon right here? It's already got 4 bonding pairs around it. If you look at it, there's 1, and there's 2, there's 3, there's 4. So this carbon right here already has a formal charge of 0, so there is no hydrogen implied there. So that's just a carbon. Okay, now let's take a look at the oxygen atom. An oxygen atom, okay, has 6 valence electrons by itself, right? So a free oxygen atom has 6 valence electrons. So the way for oxygen to bond and end up getting a formal charge of 0 would be for it to just form 2 single bonds. See, that's going to be, if it forms 2 single bonds, it's going to own 2 plus 2, that's 4, okay, plus half of the 2 pairs would be 2 singles, it's going to own 6. Appear to own 6 in the structure, so 6 minus 6 is 0. So oxygen, we say, can form bonds and have a formal charge of 0 if it has 2 bonding pairs. Okay, so 2 bonding pairs for oxygen, and so that means it either forms two single bonds. So the typical bonding pattern for oxygen is 2 single bonds or 1 double bond, and then implied there is that it has 2 lone pairs. So this oxygen right here, okay, it's already got two bonding pairs. It's got a double bond. So the only implied structure here would be you have 2 lone pairs on this oxygen. The only implication here is that this particular oxygen has 2 lone pairs in addition to that double bond. How about this oxygen right here? This has a formal charge of -1. Okay, what does it mean if an oxygen has a formal charge of -1? That means it appears to own 7 valence electrons, right? 6 by itself, it would appear to own 7. So we have to draw this structure here. If you want to completely draw this structure right here, you have to show oxygen appearing to own 7 valence electrons. And the way you do that is you put 1, 2, 3 lone pairs on the oxygen. That gives it an octet. Okay, so it's a bonding pair and 3 lone pairs gives it a total of 8 valence electrons around it. So you can see it now appears to own 6 in the 3 lone pairs, okay, plus half of the bonding pair, which is 1. So in this case, it appears to own 7. So that's what's implied. So that's what's implied when you put that negative formal charge on the oxygen. And finally, this nitrogen over here, okay, you can see it's got a bonding pair with a carbon, and then you got 3 hydrogens attached to it. That means it's got 3 single bonds with a hydrogen, okay, because we know that hydrogens cannot form more than 1 bond. So each hydrogen must be bonded to that nitrogen. And then the plus there indicates that it has a formal charge of +1. And in fact, that's the case for nitrogen. You see, a free nitrogen atom would have 5 valence electrons. It belongs to group 5. And in this particular structure, it appears to own, it's got 4 bonding pairs. So 1, 2, 3, 4. Half of the 4 pairs would be 4 singles. So 5 minus 4 would be +1. So anytime nitrogen has 4 bonds around it, it has a formal charge of +1. Okay? Now, for nitrogen to have a 0 formal charge, it will have to have 3 single bonds and a lone pair, or double bond and a single bond and a lone pair. So it needs 3 bonding pairs, or a triple bond and a lone pair. So these are the typical ways that nitrogen, oxygen, and carbon will bond. And you'll see a lot of molecules that have carbon, hydrogen, and nitrogen, and oxygen. So these are things you really need to be familiar with. Okay? All right. So here's a skeleton structure for something kids like to drink. This is the red dye that they use to color Kool-Aid. So in this structure, okay, what's implied in this corner right here? That's a carbon atom that's implied there. And that particular carbon atom has a double bond and a single bond sticking out of it. So it's already got 3 bonding pairs. That means there's an implication that there's another bonding pair sticking out of that carbon, and that bonding pair is bonded to that bonding pair of electrons is shared with a hydrogen atom. So there's a carbon implied there and a hydrogen attached to it. Okay? This end right here, okay, this end of this part right here implies there's another carbon atom there. Okay? So there's a carbon atom here, and since it's got 1 bonding pair, that means it's implied that that particular carbon has 3 other bonding pairs, and at the other end of those bonding pairs would be a hydrogen atom. Look at this oxygen right here. This oxygen has a bond with a carbon on the other side, right? So remember, there's a carbon at this end, and it bonds with a hydrogen. So this particular oxygen right here has 2 bonding pairs, 1 and 2. So that means, and it doesn't show any formal charge, that means it has 2 bonding pairs and 2 lone pairs. Right, so that's how you would interpret skeleton structure. Look at this nitrogen right here. All right, if you look at that nitrogen, this nitrogen has a double bond on this side, a single bond on the other side, and has no formal charge, right? So 0 formal charge. That means, okay, it's got 3 bonding pairs. So that means it must have a lone pair. Okay? So for nitrogen to get a 0 formal charge, it must have 3 bonding pairs and a lone pair. Okay. Now, the octet rule, as I said, is just a general pattern that's observed, but that's not a strict rule. So there are exceptions. For example, data suggests that molecules containing boron and beryllium can be better represented by structures where boron or beryllium has less than an octet. Let's try BeH2, for example. The only way you can do BeH2 is to put beryllium between the 2 hydrogens. So it just has 2 single bonds. So this beryllium has only 2 pairs of electrons around it. So it only has 4 electrons surrounding it, 4 valence electrons. Okay. So BeCl3 on the other hand, BCl3, boron trichloride. So what you would do is surround it by 3 chlorines. Okay, typically when you have formulas of this type, you have one atom of one element and several atoms of another element. Your best bet is most likely you'll find those to be uh, uh, where you have one central atom and all the other atoms are just bonded to that central atom. So this is your initial structure for BCl3. If you look at your periodic table, boron has 3 valence electrons. Each chlorine has 7. So 7 times 3, that's 21. You need a total of 24 valence electrons. So the way you complete this structure is you look at we call these terminal atoms or ligands. Okay. Ligands means it's tied to something, so it's tied to the central atom. And you complete the octet for those unless it's hydrogen. So this chlorine needs an octet, so it's already got 2, 4, 6, 8. So you draw 3 lone pairs around it. This chlorine has 1 bonding pair, so 2, 4, 6, 8. All right, and this chlorine has 1 bonding pair, so that takes care of 2, 4, 6, 8. Now this completes the structure because now you can see you've got an octet here, that's 8 plus 8 plus 8, that takes care of 24. And you can see boron is only surrounded here by 2, 4, 6 electrons. Boron in this case doesn't have an octet. Okay? Now you might say, is it possible for boron to get an octet if we move one of the lone pairs? Yeah, you could. You can say boron could have a double bond with one of the chlorines. Okay? So now you have an octet around the boron. Okay, you have 2, 4, 6, 8 around the boron, and you still have an octet around each of the chlorine. Problem with this is you end up with a -1 formal charge on boron and a +1 formal charge on chlorine. Okay, whereas in this structure here you have 0 formal charge on boron and each of the chlorine. So this is less likely to happen. Chlorine is more electronegative than boron. Most likely the electrons would, if you have shared electrons between boron and chlorine, they would prefer to stay with the chlorine. Okay? So that's one exception. Here's another exception. There are some molecules that are just as they exist in nature have molecules that have an odd number of electrons. So if you have an odd number of electrons, there's no way you can pair them all up. So for example, nitric oxide, the molecule NO, has 5 from nitrogen and 6 from oxygen. That's 11 valence electrons. And this is the best way we can draw the Lewis structure is one of these atoms would have an unpaired electron. Okay, so oxygen here is an octet. There's 2, 4, 6, 8. Okay, and this nitrogen in this structure would have 2, 4, 6, and only 7 valence electrons around it. All right, so that's your nitric oxide molecule. And here's another way of distributing it. This time here you have nitrogen with the octet, and the oxygen has 7 valence electrons around it. So these are what we would call resonance structures. Okay? There's 2 possible ways of distributing the electron. Now, these types of molecules are generally very reactive, okay, and that's a characteristic of molecules that have an odd number of electrons. Because they tend to seek out another electron, you might say. So they're very reactive, and experimental evidence for the existence of the unpaired electrons would be paramagnetism. These molecules would respond to magnets. That's a sign that you have an unpaired electron, at least one unpaired electron in your molecule. So which of these 2 resonance structures do you think is more significant, more plausible? What you need to do is you look up your formal chart. You figure out your formal charges. So let's figure out the formal charges here. This oxygen has, by itself, oxygen should have 6. And here it appears to have also 6. It's got 2 bonding pairs and 2 lone pairs. So formal charge of oxygen here is 0. The formal charge of nitrogen here is also 0. Whereas here, the oxygen appears to own 2, 4, 6, 7. So here you have, I'm sorry, 2, 4, 5. Okay, so by itself, oxygen will own 6, but in this structure, it only appears to own 5. So that's 2, 3, plus half of the 2 pairs, so that's 5. 6 minus 5 is plus 1. So the formal charges here are plus 1 and negative 1. So you can say then that this will more closely resemble the way the electrons would be distributed in a nitric oxide molecule. And you can see that when nitric oxide reacts, it's this nitrogen end that tends to be the part that reacts with other molecules or atoms. Okay. Now, another exception to the octet rule would involve atoms that are beyond the second row. Okay, so second row atoms, the most they can do is get an octet, but beyond that, third row and below, these atoms down here can actually have what's called an expanded octet. They can have more than an octet around them when they share electrons. And the reason for that is because their outermost shell, okay, for the second row, for example, the outermost shell is n equals 2, right? Or the valence shell for the second row is n equals 2. Now, if you remember from your electron configurations, 2s and 2p subshells, okay, there's only the second shell has only 2s and 2p subshells. And your 2s subshell can hold as much as 2 electrons. Your 2p subshell can hold as much as 6 electrons. So the most you can accommodate in the second shell would be 8 electrons. That's sort of the rationale for the octet rule. But once you get to the third row and beyond, when you get to the third shell, for example, okay, when you go to n equals 3, then you're going to have 3s, 3p, and 3d orbitals. So that's 2 plus 6 plus 10. You can actually accommodate up to 18 electrons. In fact, these transition metals right here, they can actually form covalent bonds, okay? They can form covalent bonds, and they can accommodate up to 18 electrons. There's what's called an 18 electron rule for compounds involving transition metals. All right. So based on that, let's take a look at this question right here. Which atom cannot have more than an octet? What would be the answer to that? Is it A, carbon, or B, silicon? Which one cannot have more than an octet? Do a quick clicker check on this one. Okay. All right, what did we say? Second row elements. About the second row elements, the valence shell is 2. The most that I can have is an octet. So this carbon cannot have more than an octet. Okay. But the silicon can, because silicon is in the third row. So it has 3s, 3p, and there's a 3d orbital where you can put the additional electrons in. All right? So let me try another question. Chlorine. Can chlorine have more than an octet? Yes or no? The answer is yes. Okay, so can sulfur. But oxygen is in the second row. It cannot have more than an octet. Can hydrogen have an octet? No, hydrogen, in fact, the only thing hydrogen can do is have a duet, right? One more electron, because then that would fill up the first shell. So the outermost, the valence shell of hydrogen is the first shell. So in a 1s orbital, you can only accommodate up to 2 electrons. All right. Now, expanded octets actually allow us to avoid large formal charges, and this actually tends to happen more than we might think. So, for example, consider sulfate ion right here, okay? Sulfate is SO4 with a -2 charge. So if you were to draw something like this, like I said, anytime you have a formula where you have one atom of one element and several atoms of another element, your best bet is just to surround the first one by the other. So you have sulfur here surrounded by oxygen. Okay, hold on here. And in the case of sulfur, all right, so you surround it with oxygen. But if you look at this structure right here, you'll find, okay, first of all, let's make sure we have the right number of electrons. Sulfur by itself should have 6, right? So contribution of 6 from sulfur, valence electrons. Oxygen should contribute 6 times 4. That gives you 24 valence electrons for a total of 30, right? And there's a -2 charge, so that's 2 more. We need 32. Right? So the strategy is you surround your sulfur by oxygen. Okay, that's step 1 for drawing the Lewis structure. And then you give each of the ligands, each of the terminal atoms an octet. So this oxygen gets, so it's already got 1 pair, 2 pairs, 3 pairs, 4 pairs. It's got an octet. This oxygen already has 2 valence electrons shown as a bonding pair. It's going to need 6 more, so 2, 4, 6. This one has 2, 4, 6, and that would be the 8th one. This one would also need 3 lone pairs. And that's what we have right here. And the total charge would be -2. But we're not done here yet, because as you can see, if you look at your formal charge, let's examine what the formal charge is going to be. Okay? If you examine the formal charge for sulfur, you'll find that by itself, a free atom of sulfur should have 6 valence electrons. But how many does it appear to own in this structure? You'll see that it's 2, 4, 6, 8. Okay, half of 8, half of the 4 pairs would be 4 singles, so it appears to own 4 electrons in this structure. So 6 minus 4 is going to give you a formal charge of +2. Okay? Formal charge of +2 is not good. How can you lower that formal charge? You put more electrons towards the sulfur. So what you can do is you can, for example, move one of these electron pairs. Instead of that being a lone pair, you can make that a bonding pair, a shared pair between oxygen and sulfur. That would push more electrons towards sulfur. That would lower the formal charge on the sulfur. So if you have, that would lower it to +1. And you push one more, you can form 2 double bonds here, okay? And you can see that your sulfur here ends up having a 0 formal charge. So let's take a look at this particular sulfur right here, this way of drawing the structure. So sulfur, a free atom, has 6, right? And how many electrons does the sulfur atom appear to own here? It's got 1, 2, 3, 4, 5, 6 bonding pairs around it. What's half of 6 bonding pairs? 6 singles, right? So the sulfur here appears to own 6 valence electrons. So 6 minus 6 is 0. So the sulfur here has a 0 formal charge. Okay? We say that this particular sulfur, the way this structure is drawn, has a 0 formal charge, and so that's good. We like that. Okay, so that's a general strategy you can use. There's a website. The way to be good at drawing these Lewis structures is really to just practice. There's a nice website where you can do a lot of practice tutorials that you can go through. I posted that on the free Moodle site under the Internet Resources for Lewis Structures and Molecular Geometry. And you go to treefrog.fullerton.edu, okay, or you can just do a search, okay. So let me see if I can do a search here. You can do treefrog.fullerton.edu, all right, and right here there's animated tutorials on how to draw Lewis structures. It's best to use Internet Explorer for this site. Okay, and here, let's say you wanted to draw the Lewis structure for sulfate. Okay, as I've shown you earlier. Here's sulfate ion. There's the Lewis structure. Here's a step-by-step tutorial. You're going to need a plugin for your computer called Shockwave. Alright, so here's a step-by-step tutorial for drawing the Lewis structure of sulfate. Okay, so first you count the electrons. Okay, sulfur. Hold on. Let me put it back. Let's see. Try it again. Okay. Alright, so let's go back. So first you count the electrons, sulfur, oxygen. So that's 1 sulfur, 4 oxygens, and a -2 charge. So sulfur, it belongs to group 6A, so it has 6 valence electrons. Oxygen also belongs to group 6A, so it has 6 valence electrons. 4 times 6, 24. A -2 charge means 2 additional electrons. Okay, so it explains it to you step by step. You have 32 total electrons, that's 16 pairs. Okay. And then it shows you have sulfur, has to be surrounded by the oxygen. Okay. You could call this the type AB4. 1 atom surrounded by 4 other. You position the central atom. You arrange the ligands, the terminal atoms around the central atom. So that's, so you have 16 pairs to distribute. You form 4 single bonds around the central atom, okay? And then you give each of the ligands an octet. That gets an octet. That oxygen atom gets an octet. And this last oxygen atom gets an octet. And then you hit continue. Calculate formal charge. And you find that in the case of sulfur, it has formal charge of +2. And you see, label the sulfur with the formal charge of +2. Same thing for the oxygen. So all the oxygens have a -1 formal charge. Okay. Now, a formal charge of +2 is not good. So what you do is you move some of the electron lone pairs from the ligands to bonding pairs between the central atom and the ligand. Okay. So you can have up to 2 double bonds, so you can lower your formal charge. Okay. You want your formal charge to go to 0 if you could. Okay. And then you can see you can move another double bond, another lone pair into a bonding pair, and it becomes a double bond. So you have the correct Lewis structure has 2 double bonds, 2 single bonds, but this is just one of many possible resonance structures, because you could have done the double bond here and here, or here and here. Okay, so 2 of the bonds are double bonds and the other 2 are single bonds. What that suggests is reality is the hybrid is probably not that. It would be a hybrid of all those possibilities. So you have 4 equivalent bonds, which would be, you might say, 1.5 bond, right, rather than a double bond or a single bond. Okay. So that's exceptions to the Lewis structure, to the octet rule. So here's a quick review. Which of the following atoms must have an octet when sharing electrons with other atoms? You have to look at your periodic table for this one. So what's the answer? Okay. The answer is, which of these must have an octet? None. Why none? Remember we said the octet rule is not a strict rule. In fact, boron's an exception. We've seen an exception for boron. BCl3, remember, didn't have an octet. Nitrogen, we've seen an exception, right? It doesn't have to have an octet. So not having an octet doesn't mean your structure is wrong. It simply means, if you, that's not something you, that would not be the first thing you would guess, you would imagine happening, okay? So that's just a guide. And sulfur, for example, can have an octet, expanded octet, anything beyond the third row. So carbon doesn't have to have an octet, okay? Um, so you can have radicals for carbon, for example. This won't be a molecule, it's called a radical, CH3 with one unpaired electron. It's a very unstable species. Okay. Let's take a look at this one. Which of the following atoms can have more than an octet when valence electrons when it shares electrons with other atoms? Is it sulfur, nitrogen, carbon, or hydrogen? Very good. Sulfur. Third row and beyond, you can have more than an octet. Good. Okay, so now let's talk about molecular geometry. Maybe. Molecular geometry deals with shapes of molecules, and we use a theory known as VSEPR, VSEPR, valence shell electron pair repulsion theory, to predict shapes of molecules. So when we draw the Lewis structure, all we're trying to do there is we're just really showing how the electrons could be distributed, the valence electrons could be distributed among the atoms of a molecule. Now, you should not take those literally as the actual shape of the molecule. To determine the shape of the molecule, you have to think about the fact that these groups of electrons sticking out of an atom would be trying to repel each other. Okay, so the basic idea in VSEPR is that you have groups of electrons around an atom. They tend to be oriented as far away from each other as possible, and that's because electrons repel each other. Okay, so for purposes of determining molecular geometry, the shape of the molecules, we count each group of electrons around an atom. We count a single bond as just one group of electrons around the atom. A lone pair counts as one group. A double bond, all 4 electrons in a double bond, we count that as one group. Okay, so each group of electron around an atom is called an electron domain. So these electron domains, okay, for us to be able to predict the shape of the molecule, we have to imagine that each of these electron domains has to repel the others, and so they're going to try to stay as far away from each other as possible. So the word steric number refers to the number of electron domains around an atom. So what's the steric number around each atom in the structure shown here for urea? Let's look at this carbon atom right here. Okay, this double bond counts as one electron domain. That's one group. This single bond is another group, and this single bond right here is another group. So carbon here has a steric number of 3 for carbon. Okay, so that's for carbon. For nitrogen, let's look at this nitrogen. What's the steric number for this nitrogen? It will be 1, 2, 3. So that's 3 bonding pairs, 3 single bonds, and the lone pair counts as another group. So the steric number for nitrogen here is 4. Okay, what's the steric number for oxygen here? That lone pair counts as one group, that lone pair counts as another group, and this double bond counts as another group. So for oxygen, the steric number is 3. Okay? Steric number simply refers to the number of electron domains around the atom. And VSEPR says those electron domains will have to try to stay away, as far away from each other as possible. So what if you only have two groups of electrons sticking out of an atom? Then you can predict the shape of the molecule, because then you're going to say those two groups are going to be pointing in opposite directions. So they're going to be 180 degrees apart. So if you have an atom, a molecule that has two single bonds only and nothing else, then those two single bonds have to be oriented as far away from each other. Or if you have a single bond and a triple bond, or two double bonds, okay, if those are the only groups sticking out of an atom, those two groups have to be 180 degrees apart. So we say then that the atom in this particular case, if the steric number for an atom is 2, we say it's a linear center. See, it's a straight line between those two groups. Okay? And the geometry, the electron geometry, domain geometry around X is linear. Okay. So if the steric number is 3, then for them to stay as far away from each other as possible, those three groups must be 120 degrees apart. So it's 120, 120, 120. Remember, full circle is 360. So that's a 120 degree angle between them. Right? So if you have, for example, a double bond right here, let's say you have a carbon atom that has a double bond and two single bonds, okay? Like formaldehyde, for example. Then this angle, right, if I were to ask you what is this angle right here, it would be close to 120 degrees. Okay? Now, it's going to be exactly 120 degrees if all the groups are identical, but like in this particular case, this double bond is a little bulkier than the single bonds. So what these two angles here are actually going to be slightly larger than 120. Okay? So this should be slightly larger than 120. Because you have more electrons in a double bond, so it would tend to push these single bonds a little closer together. So this angle over here is going to be slightly less than 120. But, 120 should be just fine for approximate purposes. Okay? And then if you have a single bond, a double bond, and a lone pair, that's, again, 3 different groups. So approximately they're going to be 120 degrees apart. Now, these 3 groups are going to be sticking out towards the corners of a triangle. So if there's an atom over here and an atom over here and an atom over here, what's the shape of the molecule? You say your molecule is a triangular or trigonal planar. Okay? So all the atoms are on the same plane. Okay, and the groups of electrons that are sticking out of your central atom are sticking out towards the corners of a triangle. So X right here we say is a trigonal planar center. So it's the center of a triangle on a plane. Okay? So this X right here is also a trigonal planar center. So here's an example of an ion that has a shape that's called trigonal planar, carbonate. So here's the lowest structures of carbonate. These are resonance structures. Okay, you got this carbon atom has a steric number of 3. 1, 2, 3. 3 groups of electrons are on it, 3 electron domains. So if this is carbon, you have your oxygen here, oxygen here, oxygen here. That angle is 120 degrees. Let me show you a website where you might be able to get a better view of this, visualization of this. You just go to phet.colorado.edu and you do a search for molecular shapes right here. You run that Java applet. Where is it? What happened to it? Oh, okay, there's a warning. So if you have 2 groups of electrons, you can show the bond angles is 180. See? There's a 180 bond angle right there. Okay. that angle. Right? So the geometry of this molecule is linear, and the electron geometry is also linear. Electron geometry refers to the orientation of the electrons sticking out of your central atom. Now, if you're going to have three single bonds around the atom, okay, and so you can see all of these atoms are on the same plane, and they're at the corners of a triangle, right? That's your triangle right there. So the molecular geometry is called trigonal planar. The electron pair geometry is called trigonal planar. There's 3 electrons sticking out of your central atom pointing towards the corners of a triangle. So that's a trigonal planar geometry around the central atom. The shape of the molecule itself is trigonal planar. But what happens if one of these groups is not a single bond? So if I'm going to remove a single bond from there, instead I'm going to put a lone pair, okay? Here you still have a steric number of 3. You still have 3 groups. 1, 2, 3 groups sticking out of your atom. So this one right here is just a lone pair. Since there is no atom over there, anytime you only have 3 atoms, you describe the shape of the molecule in terms of what the shape is of the 3 atoms. Okay, so if I were to make the lone pair here invisible, there's a lone pair there somewhere, right? Okay. Then we say that the shape of this molecule is bent. So anytime you only have 3 atoms, either the atoms are on a straight line or they're not on a straight line. So if it's not on a straight line, the shape of the molecule is bent. Now the geometry around the central atom is still trigonal planar. The fact that this thing is bent tells you that there must be another group sticking out here, and that's the lone pair. Okay, I'm sure the lone pair is going to show up there. All right, so that's 3. What if the steric number is 4? Let's add, okay, let me remove that lone pair and let me just add 4 single bonds. I have 4 single bonds. You have a 3-dimensional structure. The best way to get these groups as far away from each other as possible is to have what's called a tetrahedral structure. Okay, why is it called tetrahedral? Tetrahedral. The reason for that is, imagine this one right here, that's one face of a pyramid, okay? You have 4 triangles, okay? And there's a triangle at the bottom. So those atoms, okay, the groups of electrons sticking out of the central atom are pointing towards the corners of a pyramid, a perfect pyramid. Okay, so it's a pyramid is a 4-sided figure. So tetrahedral means 4-sided. Tetra means 4, hedron means side, so it's a solid figure that has 4 sides. So we say the groups of electrons sticking out of your central atom are pointing towards the corners of a tetrahedron. So we say your central atom geometry, or your electron geometry for the central atom, is tetrahedral. If there's an atom at each one of those corners, then that means your structure, the shape of your molecule, is also called tetrahedral. Now these angles are 109.5. You can show that using geometry. You can measure that angle if you want. Okay. It's going to be 109.5. Now, what if one of these groups happens to be a lone pair? So I'm going to have 4 groups now, and one of them happens to be a lone pair. Okay, so it's still tetrahedral geometry, right? There's still 4 groups sticking out of your atom, of your central atom. So there's 1, 2, 3, 4 groups still sticking out of your atom. It's still tetrahedral, but look at the name of the molecule, the shape. The name of the shape for the molecule. It's not tetrahedral anymore. You call that trigonal pyramidal. So it's still like a pyramid. It's like a flattened out pyramid. You're only looking at the shape that's defined by the atoms. You ignore the lone pair. Okay, so I'm going to hide the lone pair here. So you can see that. So if these angles are 109.5, then this looks like a pyramid, right? But there's a lone pair out there that is not used as part of this, the description of the shape of the molecule. So when you're describing the shape of the molecule, you just describe the shape that is defined by where the atoms are located. Now, one thing you have to realize about these shapes is these are the average locations of the electrons. An actual molecule is not really stationary like this. These bonds are actually going to be stretching, okay, and compressing. So this is going to be oscillating back and forth. It's going to be bent. These angles are going to be bending. So this is going to be these angles are going to be changing. So what you're describing here is just the average locations of the atom, their average orientation with respect to each other. Okay, so that's 4. Okay, and if you have 5, what you get, so let me go ahead and remove the lone pair and then do 5. If you have 5, you'll notice 3 of those are on a plane. Okay, 3 of those groups, 1, 2, 3 groups are sticking out towards the corners of a triangle on a plane. Okay, the 4th group is on top. The 4th group is sticking towards you. The 5th group is sticking away from you. All right, so so this is trigonal bipyramidal. Let me turn this around. You can see there's your trigonal bipyramidal structure. So there's your trigonal planar groups. Okay, these are, you can imagine this would be the equator of the Earth. Okay, so these 3 groups right here are called your equatorial groups. And you can imagine the 4th and 5th group as sticking out towards the North Pole and the South Pole. So you have 2 axial groups. Axial means along the north-south axis. Okay. And you have 3 equatorial groups. So what are the angles here? The equatorial groups are 120 degrees away from each other, right? And so as you've seen earlier, let me turn this thing around. Your equatorial groups are 120 degrees from each other. Okay, that's 120, that's 120, that's 120. And, oops, sorry. Compared to the axial groups are perpendicular to the equatorial groups. So that's a 90-degree angle there, that's a 90-degree angle there, that's a 90-degree angle right here. Okay, so those are the angles in this geometry. We call this trigonal bipyramidal. Why trigonal bipyramidal? You can imagine that here's a triangle right here. That's the base of a pyramid that's right side up. And that would be the base for another pyramid that's upside down. Okay? So there are 2, it's like you have 2 pyramids, one sticking up, pointing upwards, the other one pointing downwards. So it's trigonal bipyramidal. So if you have 4 groups sticking out of an atom, you have a trigonal bipyramidal geometry. The shape of the molecule, if there's an atom at every corner, at the end of each group that's sticking out of your molecule, of your central atom, then you have a trigonal bipyramidal shape for the molecule. Now, what if one of those groups is a lone pair? A lone pair, okay, a lone pair is bulkier than a single bond, so it would try to find a location that would be as far away from the other groups as possible. And the preferred location for lone pairs are the equatorial groups. So if one of these groups happens to be a lone pair, okay, so there won't be, you'll have one missing atom, right? And you'll have one extra lone pair. Oops. Add a lone pair. So I've got a lone pair and 4 groups, right? Look, the lone pair took one of the equatorial positions, okay? And so you can see, okay, there's your lone pair taking up one of the equatorial positions. You still have your 2 axial groups and your other 2 equatorial groups there. So if I were to make this lone pair invisible, what shape do you see here? This is a seesaw. The shape here is a seesaw shape. Okay, so here's your fulcrum right here. Okay, So that's your shape of the molecule. So we say your geometry around the central atom is still trigonal bipyramidal, okay, but the shape of the molecule is seesaw. So that's for 5 groups. If you have 6 groups, oh, by the way, let's say another one of these groups happens to be another lone pair. Let's say you have 2 lone pairs, okay? If you have 2 lone pairs, then I take out another single bond and I add another lone pair. Let me show the lone pairs. Okay, I add another lone pair. So and the second lone pair takes another equatorial position, and what's the shape of this molecule? Looks like the letter T, right? So 2 lone pairs, there's a letter T. So we say this has three ligands, 3 atoms attached to the central atom, and 2 lone pairs. So you say this geometry is type AX3E2. Okay, the other one we showed earlier was AX4E. 4 groups around 2 lone pairs. So the E here means the number of lone pairs. Okay, so this is T-shape, and the geometry is trigonal bipyramidal. What if you have 3 lone pairs? And then the third lone pair is going to pick up another equatorial position. So if we pick up this position right here by another lone pair, then the 3 atoms would just be on a straight line. Your shape is going to be linear. So let's do that. I'm going to remove another single bond, and I have now 3 lone pairs. Look at the 3 lone pairs are occupying. Your 3 lone pairs are now occupying your equatorial positions, and so you just have 2 axial groups that have an atom on each end. But the shape of this molecule is linear. The central atom still has what we would call a trigonal bipyramidal geometry. Okay, so this would be a type AX2E3. There's 3 lone pairs, and there's 2 ligands, 2 atoms attached to your central atom. Number of ligands is also known as the coordination number. So this 2 right here, this number 2, that's also known as the coordination number, the number of ligands, the number of atoms attached to your central atom. Okay? Now let's go back to 4. There's one thing I missed with the 4. So I'm going to take out a lone pair, and now I only have 4, right? Remember, if your steric number is 4, the electron geometry is tetrahedral. There's 4 groups sticking out. But if 2 of those groups happen to be lone pairs, then the shape of the molecule, again, anytime you only have 3 atoms, the shape is either straight or bent, linear or bent. In this case, the atoms are not on a straight line. That would be bent. Okay? So that's 4. Let's do 6 this time. If you have 6 groups of electrons sticking out of an atom, let me add one more, another one. Let me take out the lone pairs for now. Okay, so that's 4, 5, 6 groups. Okay? And that's what it looks like. So all the groups are 90 degrees away from 4 other groups, and it's opposite one other group. So this shape right here is called octahedral. Why is it octahedral? Imagine you have a triangular face here, another triangular face here, another triangular face here. So you have 4 triangles on top forming a pyramid, okay? And another 4 triangles at the bottom forming a pyramid that's pointing downward. So you might say this is square bipyramidal, but the word for this is octahedral. There's 8 sides, 8 triangular sides, octahedral. You have 8 triangular sides that come together to form an 8-sided solid. So that's an octahedral figure. Okay? It's a regular octahedron. So the geometry around the atom is called octahedral. The molecule is called, the shape of the molecule is octahedral. But what if one of these happens to be a lone pair? So I'll take out one of those and replace it by a lone pair, and you end up with, okay, you got 4 atoms on a plane, okay, and then you have one sticking out at the top, so that's a square pyramidal. You have a pyramid with a square base. All right, so let me turn this around for you. So there's a 90-degree angle between the axial group with the equatorial groups, you might say. All right. Now, what if there's another lone pair? Then that other lone pair will want to stay as far away from the other lone pair as possible, so that other second lone pair is going to take the opposite side. Okay. So the shape of the molecule this time, so if I'm going to take another single bond out and I put a lone pair, you'll notice your lone pairs are bulkier groups, so they take on opposite sides. And so what you have here is the 4 groups are now just on a plane, forming a square. Okay? So the shape of the molecule is now square planar. It's still an octahedral center, but the shape of the molecule is square planar. What if you have another lone pair? Well, it has to take out one of those equatorial positions, so let me remove another bonding pair and add a lone pair. And this time the shape is going to be, oops, what would that be? A T shape, right? I can't make it, turn it to make it look like a T. There it is. It's a T shape. Okay. So this would be AX3E3. Okay. So there's 3 atoms around your central atom and then 3 lone pairs. And finally, if you have one more bonding pair, and another lone pair, then those lone pairs would be opposite each other. If you have 4 lone pairs and 2 single bonds, 2 bonding pairs, the shape of this molecule, you only have 3 atoms left, so all these atoms are on the same line. Okay, so this is a linear geometry. The shape of the molecule, we say, is linear, but the center is an octahedral center. There's actually 6 groups of electrons sticking out of your central atom. Okay, now real molecules that follow these are in this tab right here. You can see this is what water looks like. Okay, water, if you draw the Lewis structure of water, it's going to look like that. So there's 2 bonding pairs and 2 lone pairs. So for water, you have an octahedral center. Yeah, okay, so the shape of your molecule is bent. Okay, geometry around the center is octahedral. Now, if you show the bond angles, you'll see something interesting here. Water, the angle is not really 109.5. It's 104.5. Why is that? It's a smaller angle that's less than 109.5. And the reason for that, like I said, is these lone pairs are bulkier groups, and so they push those single bonds closer to each other. Okay? Now, let's take a look at ammonia. Let's see if we have ammonia here. Ammonia, NH3. Again, you have, if you draw the Lewis structure for ammonia, you're going to see that you have 3 NH bonds and a lone pair. So the steric number for ammonia is 4. 1, 2, 3, 4. You have 3 single bonds with nitrogen and hydrogen. So there's your nitrogen right here. And these are your 3 hydrogens right here. Okay? And so the actual shape of ammonia, the actual angles, if you see the numbers here, is actually 107.8. Okay, again, that's less than 109.5. Okay, and the reason again for that is this lone pair actually pushes those single bonds further away from it. So those single bonds are a little closer than they would be in a perfect tetrahedral structure. So The VSEPR model that we talk about is the idealized model. Those angles we talked about earlier are the idealized models. If you have perfect identical groups sticking out of the atom. If the groups are not identical, you get what's called distorted, slight distortions from the ideal angles, okay, from the ideal geometry. So that's NH3, and here's SF4. If you were to draw the Lewis structure for SF4, you'll find that you're going to have 4 SF bonds and an extra lone pair on your sulfur. Okay, so each fluorine will have each fluorine will have 3 lone pairs. Let's see if we have it right. Sulfur gives you 6. Each fluorine will give you 7. 7 times 4 is 28. 28 plus 6, you have 34 valence electrons. Okay, so that's 32. That's 8, 8, 8, 8. That only takes care of 32. So 2 more. You have an extra lone pair on the sulfur. Remember, sulfur can accommodate more than an octet. Okay, so there's 2, 4, 6, 8, 10 electrons are on the sulfur. So your sulfur has 5 groups sticking out of it. And so these are the 5. The 4 SF bonds. So you have your sulfur here, fluorine, 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 and there's your lone pair right there. Notice that this is not a perfect 90-degree angle. The distortion again has to do with the fact that that lone pair is a little bit bulkier than a single bond. It distorts the angle somewhat. Okay? So that's your SF4 molecule. Alright, so those are the shapes and geometries around the central atom for simple molecules, and so this is a summary right here on the PowerPoint for all of those. Okay, steric number 5, that's your seesaw, that's your T-shape, that's steric number 5, linear, so that's AX2E3. So here, for example, you have 3 lone pairs in the equatorial positions, and they have your axial groups right here. Here's your octahedral shape, and here's your square pyramidal. So you have a lone pair down here. Okay, so the shape of the molecule is a square pyramidal. And here you have a lone pair up here and a lone pair down here, but the molecule itself would be a square planar shape. All right, and so this is type AX4. There's 4 atoms attached to the central atom, and there's 2 lone pairs. Okay, so based on the Lewis structures here, which molecule is linear? Water. Is it A or B, carbon dioxide? Anytime you have 3 atoms attached, you have a triatomic molecule, the only way to describe the shape is whether the 3 atoms are lined up, it's linear, and if they're not lined up, it's bent. So which molecule is linear, water or carbon dioxide? Oops. What would be the shape of water and carbon dioxide? A is bent. Why is it bent? Because this is a tetrahedral center. Steric number here is 4, right? And here the steric number is 2. So these two, you only have 2 groups sticking out of carbon, then that means those 2 groups must be 180 degrees apart. So carbon dioxide is linear, okay, and water is bent, okay? You have 4 groups sticking out of the oxygen in water. How about this one? Which one is a linear molecule? 1 and 2, 2 and 3, 3 and 4, or 1 and 4? It's really asking what's the steric number, which one has a steric number of 2, right? Okay, 1 and 2. You have steric number of 2. 1, 2, 1, 2. So this is linear, that's linear. This is bent. And this is 1, 2, 3. So this is going to be also bent. Okay. This is a trigonal planar center. Okay. This is going to have an octahedral center. But these two will have linear centers. 1 and 2 is correct. Very good. Which of these has the smallest bond angles? We talked about this earlier. Methane would be CH4. You have 4 equivalent groups. Ammonia has a lone pair. It also has 4 groups, but one of those is a lone pair. Bond angle refers to this angle right here. Okay, this angle right here. And then you have water. So which one has the smallest bond angles? That's the angle right there. What do the lone pairs do? They push those single bonds away. Okay. Actually, this is 109.5. This is 107, and this is 104.5, as you've seen in the animation that we had earlier. Okay. Look, let me show you that. Look at your bond angles. Water. Okay, it's 104.5. You got those two lone pairs that are pushing the single bonds closer together. Ammonia. Here's CH4. This is a perfect tetrahedral shape. Okay, all the angles are equivalent. You have 4 single bonds, so all the groups are equivalent. So that you get the perfect tetrahedral shape. 109.5, and then ammonia. Okay, one of the groups is a lone pair, so you have a distorted tetrahedron. 107.8 for ammonia. Okay, so the correct answer there is the smallest bond angles in this case would be water. Okay, for the molecule represented by the Lewis structure here, okay, remember a Lewis structure does not have to reflect what the actual shape is. It just shows how the electrons are distributed. So if I ask you for an angle that says NCN here, what is this NCN angle? Okay, even though it looks like it's 180 degrees, it's not. Okay, so anytime you're asked for bond angles, you have to answer it in terms of what it would be if you were to actually look at the molecule itself. Don't rely on what's shown on the paper. Yeah, I think we need to stop after this one. So what would be the shape? What would be the angle? This nitrogen to carbon to nitrogen angle. What would this angle be? It's not going to be 180. Is it 109.5 or is it 120? 120, very good. Because the steric number around this carbon is 3. There's 3 groups of electrons sticking out of that carbon, and so that angle should be close to 120. It's not exactly 120 because this double bond is a little bulkier, so it's going to push those single bonds a little further away. So this is going to be slightly 120, but 120 is close enough. Okay? I think this is a good time to stop, and I think this pretty much ends this lesson. The rest of it are just questions.